The true nature of dark energy confounds even the world's smartest astrophysicists. Its strange anti-gravity effect is unlike anything we've ever encountered. Today, we get to the bottom of it. A few episodes ago, I asked you to take a wild ride with me into the heart of Einstein's general theory of relativity and its description of the vaster scales of our universe. Today, we get the huge payoff for our efforts. We already have some pretty awesome insights. 1. The universe is expanding, and it will expand forever. There's just too little matter in it to recollapse. 2. Such an underdense universe should be geometrically weird, a negatively curved hyperbolic hyperplane. Paradoxically, our measurements point to near-perfect flatness. This is only possible if we missed some unknown type of energy pervading all of space. And 3. The expansion of the universe is accelerating. We know this because we've mapped its past expansion history using distant supernovae. There's an unseen influence at work. We call it dark energy. This dark energy is described by the cosmological constant in the equations of general relativity. It both flattens the universe and leads to exponential expansion. But this is incredible. It means we have dark energy's number, its fingerprints at the crime scene. Knowing a possible theoretical form for dark energy will unlock many of its mysteries. Today, we're going to talk about the simplest interpretation of dark energy, one where the cosmological constant really is constant. It doesn't change over time. All of our data is completely consistent with that being true. A constant cosmological constant represents a non-zero energy of empty space, a vacuum energy. The more space you have, the more dark energy you have. It's a constant energy density. Okay, the big weird fact about a constant vacuum energy density is that it leads to exponential expansion. We saw that general relativity demands this when we looked at the first Friedmann equation. But what physical thing about dark energy is producing this outward push, this anti-gravity? That's what we're going to answer today. Now, the Friedmann equation that we've been playing with so far just isn't going to cut it. It only tells us that dark energy produces an exponential change in the size of the universe, not necessarily an exponential growth. Looking at that equation by itself, it could just as well be an exponential shrinking. To see why dark energy pushes outwards and accelerates the expansion, we need to go deeper. Its anti-gravitational effect emerges in the second Friedmann equation. The first Friedmann equation is all about the rate of expansion of the universe. The second is actually much simpler. It's about the acceleration or deceleration of that expansion. It describes the forces pushing or pulling on the expansion. Here it is. Once again, we can read this in simple English. A is the scale factor, sort of like the size of the universe. And A double dot is the rate at which the expansion is changing. It's the acceleration of the scale factor. It depends on the density here, rho. The more matter and energy in the universe, the harder gravity pulls inwards, trying to stop the expansion or speed up the collapse. That's this negative sign here. Positive acceleration outwards, negative inwards. This thing is in a real way just Newton's law of gravitation for the whole cosmos. Okay, so if rho is density, what's this P? That's the pressure due to fast-moving particles and radiation. In general relativity, energy/mass and pressure both curve space-time. The way pressure does this is pretty weird. Think about a pressurized tank. The internal gas pushes outwards as fast-moving particles collide with the walls. So if fast-moving particles produce an outward-pushing pressure, then is this how dark energy is causing expansion to accelerate? By causing positive pressure? No, that can't be it, because pressure only produces a direct force if there's a difference in pressure between two regions, a pressure gradient. In order for the pressure of fast-moving particles to create an outward push, the region beyond them has to be an area of lower pressure. But on the larger scales, the universe is pretty smooth. It's homogeneous, and so the pressure is the same everywhere. Instead, the overall effect of pressure on the curvature of space-time is a purely relativistic effect. See, high pressure from regular matter and energy means very fast-moving particles, and the motion of these particles results in a combination of relativistic corrections. The ultimate effect is that the mass of a region of the universe is higher if its particles are moving quickly, compared to a region where the particles are moving more slowly, even if the overall energy density of those regions is the same. Positive pressure pulls the universe inwards. So it looks like as long as there's anything in the universe whatsoever, that whole right side is negative. So acceleration will always be inwards. In other words, gravity is always attractive. What goes up must come down. Described this way, the universe is never static. It's either expanding and slowing down, or contracting and speeding up. This was actually Einstein's motivation for adding the cosmological constant in the first place. He wanted a static universe, so he added something to his field equations that would give a positive outward acceleration in the second Friedmann equation. Here's what it looks like. The plus sign here can counter the minus sign here. The cosmological constant was designed to work in the opposite direction to regular matter and energy. That's what anti-gravity looks like, mathematically. This is not just some math trick. Dark energy is real physical stuff. And that means its anti-gravity effect must come from its physical properties. The effect of the cosmological constant is the combined effect of dark energy's own density and pressure. So let's describe it that way. In our far future universe, regular matter will have diluted away and will only have the density and pressure due to dark energy, rho lambda and p lambda. Now, the energy density of dark energy is positive, just like regular matter. It has to be, because dark energy helps regular matter flatten the geometry of the universe. That means its density term also works on the side of matter to try to slow down the universe in the regular attractive gravity way. So dark energy's density isn't causing expansion to accelerate by itself. That leaves us with pressure. But we just discussed how positive pressure can't cause expansion to accelerate outwards. It turns out that dark energy does produce an enormous pressure. But that pressure isn't positive, it's negative. A negative P here cancels this minus sign and can result in outward acceleration. That's where dark energy's crazy anti-gravity effect comes from. It's negative pressure. What does negative pressure even mean? Well, positive pressure pushes outwards, like in our pressurized tank. So negative pressure would pull inwards. It would be like attaching stretched elastic bands between the inside walls of the tank. It's a tension. Both have positive energy density, but positive pressure pushes out, negative pressure pulls in. And we're back to that contradiction. Weirdly, the inward pulling pressure of dark energy ultimately drives expansion outwards. Again, this is due to its relativistic effect. The direct effect of dark energy's negative pressure doesn't do anything, because that negative pressure is the same everywhere in the universe. But even though the negative pressure has no direct effect, it has its relativistic effect. Relativistically, negative pressure has to do the opposite of positive pressure and results in anti-gravity. Because math. And the relativistic effect of negative pressure is actually really hard to describe intuitively. And in fact, such an explanation may not be possible. Part of the problem is that negative pressure doesn't come from the motion of dark energy particles, whatever they might be. Instead, it comes directly from the fact that the density of dark energy is constant. Let's say I'm holding a volume of the universe that has a constant energy density. If I expand it, then it has more energy in it than it did before because it has more volume. I would have to provide that energy, which means I'd have to do work to expand it. That's exactly how we define negative pressure. A volume has negative pressure if it takes work to expand, just like a volume with positive pressure takes work to compress. Negative pressure means energy is gained on expansion. That's what happens with dark energy. As the universe expands, more dark energy is created because its energy density has to stay constant. That looks like negative pressure. And yet, this abstract sounding negative pressure has a very real physical effect. It's the opposite effect to positive pressure, and it's a clear outward pushing anti-gravity effect when we look at its role in the second Friedmann equation. In the first Friedmann equation, we see it as an exponential change in the scale factor, but both agree that a constant energy density and the resulting negative pressure leads to accelerating expansion. Okay, so it takes work to expand a volume of the universe, and the energy turns into new dark energy. But who's doing that work? Where does the energy come from? The answer is maybe nowhere. Here's where intuition goes completely out the window. See, the law of conservation of energy no longer applies in an expanding universe. This law is a property of a newtonian universe in which space and time are fixed, static dimensions. In a universe governed by general relativity, this is no longer true. Energy can be forever lost or gained from nothing within an expanding, curved space-time. In a recent episode, we talked about the Breakthrough Starshot program, light sail to the stars. Let's see what you had to say. So, a few people were wondering how that probe sends its signal back to Earth. Well, the idea is to beam the data back with low-power lasers, or perhaps alternatively, to use the sail itself as an antenna for radio transmission. The signal will be weak, but we'll know exactly where to look and can use gigantic detectors here on Earth. If the signal is sent by laser, then the same phased array that projects the launch laser will also be able to spot the returning laser signal. Patrick Romo and others asked whether we could decelerate the light sail in the wind from the destination star. Well, there's actually no way to decelerate the craft. The impulse generated by the laser is many orders of magnitude greater than that of the star at the other end. No, the craft will zip through the AlphaSend system in a few minutes, recording data as it goes. And this is why you want to send a large number of craft. A few of you suggested that Moore's law is near its end. So while it's true that there's a limit to the miniaturization of silicon chips, Moore's law for computing has been roughly consistent since around 1900, with the first mechanical tabulators, followed by solid-state relay calculators, then vacuum tube computers. If we never move beyond silicon, then maybe we have a problem. But there are already multiple possibilities there. The analogies to Moore's law for laser power, material science, battery tech, etc. are also alive and well. Aging Reversed would like to spend the entire Starshot budget to cure cancer, rather than sending a speck of dust into nothing. Well, the final cost of Starshot is expected to be several billion, but that's similar to the annual budget of the National Cancer Institute and a small fraction of global spending on oncology research. If it were possible to cure cancer with that amount of money, well then we would have cured it in a year. Advances in medical research may produce more tangible benefits, but it's easy to underestimate the benefits of inspiring forward-looking projects like Starshot. They give us a sense of unity and optimism that feeds back into all of our efforts. Inspire enough smart kids to become scientists instead of bankers, and it is well worth it.